Hi, welcome to the Signal Path. It is that time of the year again, and the International Microwave Symposium just wrapped up in Washington, D.C. in the United States. Aside from all the wonderful publications and scientific work that are presented at RFIC and IMS, there's also a remarkable industry trade show, probably the biggest microwave trade show in the world, where all the manufacturers and component makers come together to show the latest and greatest they have to show for the conference. So it is always such an awesome experience to be on the industry show, and I highly recommend it if you've never attended it. Definitely at least attend it one time because it's something that cannot really be described. And I try to record one episode every year. Of course, I can only cover a fraction of what's there on the show, but in the next hour, you'll see some of the highlights that I managed to catch. I hope you enjoy it. So here we have the FSW combined with the SMW200A together working. We've seen this combination before, and here we're running VSE live directly on the instrument. But there is one thing here that is worth paying attention to, is that generally when you look at various constellations, the errors in the constellation typically look the same. So whether it's a wideband noise or some interference that's on the constellation, it's very difficult to tell what is causing the degradation. So what they've done as a new feature in the VSE is that if you add, or if you have some unknown interference, for example, I can turn that interference hard in this case, and you can see the constellation degrades. But what it does is that it simultaneously de-embeds the error of the constellation directly on the spectrum. So you can here see that there's two different kinds of interference sitting on top of each other, one of them being a strong tone present, and the other one just raising a noise floor, and that's what's causing the EVM to go down. This is extremely helpful to debug what is going on in your system, whether the noise is coming from your circuit or is coming from an interference. A pretty powerful combination. And of course, you've seen the FE series frequency extenders on the channel before. I've done a review of the 110 to 170 gigahertz version of it. This is the FE 110 SR, which goes from 70 to 110 gigahertz. Now, all of these instruments have a built-in synthesizer, and the synthesizer is sufficiently low phase noise that you can actually perform direct noise figure measurement on this. And you have a smart noise source over here, they have a filter in the front, and they have this device that they want to measure a noise figure of. And you can actually do it directly on this on an external head connected to the FSW. So it's essentially extending the capability of the FSW all the way to 170 gigahertz, even for noise figure, which is pretty helpful. And here we have the combination of the SMA100B, but of course the FSWP, one of the most capable spectrum analyzer phase noise analyzers on the market. Now, because this is a full-fledged spectrum analyzer at the same time, you get a complete spectrum information, you get cross-correlation, phase noise, and everything that comes with the FSW. But now there's also the ability to connect all the power sensors directly onto this. So in one setup, with your power measurements, you're getting spectrum information, cross-correlation phase noise measurement, extremely precise power measurement all together. So it becomes a single station for characterizing high-performance oscillators. And here we have a live wireless demo between 110 to 170 gigahertz. It's using the FE170, which I've done an extensive review on the channel. This is a fairly complex setup. A lot is happening at the same time. So we have the FE170 as a transmitter gear with its pre-select filter in the front, which is automatically embedded inside the software. And then we have a coupler over here connected to the thermal power detector between 110 to 170 gigahertz. This itself is unique in the world. This is the only 110 to 170 gigahertz banded thermal detector that has the speed and the noise floor that this particular unit provides. Then the output of that from the coupler goes into a power amplifier, and that's wirelessly being transmitted to the 170 SR on the receiver. So in one setup, you have the pre-selected transmitter, the coupler, the power measurements, over-the-air measurement, and demodulation on the other end, all together in one setup. Now, another thing to pay attention to is the release of this particular unit, the SFI100A, and this one has a built-in mixer that provides an IF output between 11 to 14 gigahertz or so. So it basically has an IQ DAC inside that upconverts into a fixed IF frequency that you can move around. The idea is that this would become the IF input for a wide range of frequency extenders that Roden Shore sells. So you can essentially buy this, connect it to this, and do modulation up to 10 gigahertz of bandwidth, anywhere in that range that you want. Pretty powerful when you combine it with something like the FE170, for example. At the same time, we do have the DAC outputs, differential, and each of those is a 5 gigahertz, and differential mode is 2.5 gigahertz. So you could use it as a standalone IQ as well if you have your own up converter or you just want to use the direct DAC outputs. So in one setup, we are not only measuring and providing extremely high bandwidth modulation, but we're also measuring precise power at the same time in one setup. Good. And so here's something new. We're using the combination of the SMW200A and the RTP oscilloscope to create an active load pull system. Now, in order to do that, you're going to use all the 4 channels of the oscilloscope and the 2 channels of the synthesizer. You would need 2 external couplers, and it allows you to actively generate the signals required to do that load pull. And because you're monitoring all 4 channels at the same time, then you can put it onto software and create your active load pull at anywhere on the Smith chart. This is a little bit under the development in terms of the software, but the hardware, of course, all works together. And the advantage here is that you can do a complete calibration ahead of time because you have all of these losses and all the signals generated under your control. And once all of that is put together, you connect your DUT over there. And at the top, you can see some analysis coming out in terms of how it looks like on the active load pull. Once the software is a little bit more refined, I think this can be a pretty powerful system because most people already probably own an SMW200A and an RTP. You just combine it on your test setup, you get a whole new measurement capability. One other item to note is that you do have 2 gigahertz of bandwidth and 2 gigabits of memory depth involved here, so you can actually do your modulation quite broad. And because of the depth, any particular memory effects that could be inside the device you're trying to do a load pull on will also be captured. But those are basically the capabilities of the generator. We're just leveraging them for the load pull capability. So here we're looking on the FSW, the demodulation, as a really, really dense constellation, 4096. You can see the EVM is minus 52 dBm, which is absolutely crazy. So one new feature of the FSW is that there's this noise cancellation capability on the IQ receiver and being able to generate this plot, but there's a particular distinction there. Whenever you're looking at a modulation constellation, what you want is you want to de-embed the noise of the instrument that's analyzing it as much as possible, but you don't necessarily want to remove the impairments coming into the analyzer, because that's from your circuit, that's from your device. You don't want to cancel that. So what they do here is they actually terminate the input of the spectrum analyzer periodically and measure its own internal noise and correlate that with the signal coming in so they can de-embed the noise of the instrument analyzing it as much as they can without affecting anything coming from the DUT. So what you end up with is kind of a quasi-perfect receiver, giving you this beautiful constellation, but maintains the imperfections of the constellation coming into the unit. And that's a pretty important feature. You can see how great this constellation measurement is, and that signal is being generated with the SMW200A, which we see all over the floor. And here's the new facelift on the SMW200A. As you can see, it looks a little bit different, more modern, matching the rest of the latest instrument. But it also has not only all of its frequency calibration characterization, which is typical for synthesizers, but it also has its nonlinearity coefficients factory calibrated inside the unit. So what this means is now you can push this to higher output powers across all of its frequency range and output power because it will apply the DPD algorithms directly inside the unit. So what comes out has that already embedded inside because it's been pre-calibrated. This of course means that the calibration coefficients of this unit must be quite a bit larger from the factory to accommodate for the nonlinearity as well. But this means that you get a lot more use out of the SMW without requiring external amplifiers, and particularly without having to linearize anything on the external amplifiers. And given that we are in Washington with a lot of defense contractors around, this is a particular deployable combination of the FSW and synthesizer together at the same time. So what this is essentially is a mobile, really broadband, really low noise, software-defined radio. There's almost unlimited storage at the top behind the screens. You deploy this in the field, you listen, you capture everything, you IQ stream everything at the highest rate, store them, and then you can pick it up and leave. And then you can analyze all kinds of signals that were present at the time where you actually measured. So if it was radar, if it was some communication, if it was some jammer, you'll be able to capture that, store it, and get out of the environment that could be potentially hostile. This combination is obviously intended with the boxes that you can see to be ruggedized so you can deploy it quickly. But yeah, I'm sure a lot of defense people like stuff like this. And here we have the ZNA, this time connected with the frequency extenders between 110 to 170. Of course, the ZNA, you should now know, this is the ultra-high dynamic range network analyzer base, which can be connected to all these extenders. Now, 110 to 170 gigahertz extenders in this case are actually two-tone generators, so there's 2 up converters and down converters in each one, so that of course gives you OIP3 measurement, IM3 measurement directly from the units themselves. Now at the same time, because you want to measure nonlinearity, things like compression, you would need to do a power cal, and doing a power cal at 110 to 170 is quite difficult, and of course we're going to do that with the new NRP sensor, which you've seen me show also on the channel, a thermal detector, extremely fast, allowing you to power cal across a wide range of output frequencies and powers directly on the units themselves. So you do a power cal, you connect it up, and then in one station with the ZNA, you can do everything at D-band that you could do below 40 gigahertz, which is crazy to think about, that you could do all those measurements in exactly the same setup. So pretty powerful, and I believe that Roden Shores is basically making these now themselves, kind of separating themselves a little bit from the other vendors that use other parties' extenders. And of course, once you make your own with your own firmware, it just ties together, it works so much better. And here we have Keysight's active load pool setup. It's interesting that this year both Rodenshorst and Keysight are simultaneously showing an active load pool. And of course, Rodenshorst's setup we just saw was different. They were using an oscilloscope. Here we're using the receivers of the PNAX for that. The PNAX has some pretty good receivers, so you can get really good digitization, but the magic of the transmitter comes from the VXG, the new platform that they have. We have broadband signals generated both from the 2 channels of the VXG, going into the couplers and into your device under test. So now, once you have this set up together, there is a lot you can do. You can download profiles of the impedances you want to go through, but not only that, the PNAX can actually do demodulation and perform EVM measurements too. So all of a sudden, you're going to get these curves, the curves of output power frequency across the load pool circles that you actually want to cover. Or if you want to measure this, let's say in a phased array situation, and you have the active return loss characteristics of your antennas during steering, you can download that profile, and now you're pushing your power amplifiers during the active return loss during steering. So you can then train your systems for DPD if required. You want to make sure you're resilient towards the different loads that are there. But the combination of the PNAX and the VXG for doing EVM measurements in DPD is not new, that they've definitely shown that before. But with the appropriate software in the background, now you can do all this active load at the same time. More and more we see that the combinations of the instruments from basically all the big vendors are becoming this powerhouse of these strong characterization platforms. With the right software, you can pretty much do anything. And here we have an active live measurements on IQ correction. We have the VXG, which is generating IQ data into an up converter into the V3050, which is a down conversion, of course, going into the UXA. So what this setup allows you to do is to calibrate all the IQ impairments and all the phase and offsets between IQ on any transmitter that you have by going through all the frequencies ahead of time and then pre-correcting that waveform and then feeding it back to your signal. So this has 2 advantages. First of all, it allows you to measure constellations which may have had very poor EVM due to IQ imbalance only and image rejection problems, but it also allows you to extract the correction data separately so you know exactly what your circuit was doing. So in a way, you're characterizing IQ impairments across the broad frequency range that is supported by the VXG and the V3050 simultaneously. This is a pretty helpful thing because most of impairments on EVM on these millimeter wave transmitters, for example, comes from a lot of combined effects. There's noise, there's nonlinearity, there's IQ imbalance, and so on. And being able to separate them and de-embed them from each other is a really powerful platform. So this entire setup running live is doing that in the background. And here we have the Keysight's antenna chamber characterization. I think this is the first time I've seen that at the show, that they brought this entire thing. This box is supporting up to 110 gigahertz, but the fundamental principle is the same. It's doing near field to far field translation with a reflector inside the box, which we will see in just a moment, and it allows you to calibrate up until the surface of your array or your transmitter. This technique is common, but it's extremely helpful in a very compact area to perform tasks at frequencies which would require a very, very large distance to be in the far field of any particular antenna or array that you may have. This is coupled with, of course, their PNAX and VXGs for generating signals. So not only are you, for example, characterizing ERP and various other emissions, but you can also capture waveforms and create constellations directly in what the constellation would look like in far field after correction with a reflector. So we'll open up the chamber once this simulation and measurement is done so we can take a look at that. But this is basically competitive to the other boxes we've seen from Rodenshorst. And here we have the SSAX signal source analyzer. The 54 gigahertz version of this was finally announced in January. This is an interesting instrument because it's a multiple different capabilities in one. It can do network analyzer, phase noise analyzer, VCO analyzer, and of course it has cross correlation capability. And because of that, there is a lot of unusual setups you can put together and measure a lot of things at the same time. So for example, here we have the VXG. This is a 2-channel VXG. These are very, very low phase noise instruments, and they're generating 2 signals at 12 gigahertz. Now, one of those signals directly goes into the analyzer. So, of course, we can measure its phase noise with cross-correlation. You can see how good the phase noise of this is. But on the other path, we're doing an up and down conversion. So we're taking the 12 gigahertz, going all the way to D-band, and then going all the way back from D-band, and then putting that into the instrument. So you can imagine this multiplication has a penalty on the phase noise of the signal, and then we can de-embed that penalty directly on the signal source analyzer as well. So this combination is powerful because you often don't know what happens to your signal in such complex multiplications, and you can de-embed all of that. At the same time, because we do have a network analyzer functionality as well, you can do gain compression measurements of various devices under test in the same connector front end that you were doing before, or you can figure out with the built-in really low noise sources inside of the SSAX, what is the added phase noise of particularly amplifiers in the frequency range all the way up to 54 gigahertz. This unit is actually a lot smaller than I thought it would be. because it's quite a bit smaller than the UXA. But yeah, there's a lot of functionality in here. You can see the ultra low noise quiet DC sources in here for characterizing VCOs. Keep in mind that signal source analyzers actually lock the VCO and de-embed and figure out its CV characteristics while it's running. So this is basically a souped up version of the original signal source analyzer that Agilent and HP used to make. So very powerful instrument, so hopefully we can get a look at it at some point. And here at Siglent Hound, we actually now have a signal source analyzer set up using their broadband SM435 real-time spectrum analyzers. So the idea is fundamentally quite simple. If you have two of these spectrum analyzers, you can connect it to this new box, the PN400, which has the gating as well as the signal splitting built into it, and it also has the low noise voltage sources, so for VCO characterization. So this becomes the front end of a cross correlator for phase noise analysis, and the signal then directly goes into two of your spectrum analyzers. Now, most people have multiple of these because you want to deploy them in different scenarios. So in this setup, you can quickly create a phase noise analyzer without having to commit to a dedicated phase noise analyzer box. And if you buy them as a bundle, I think there are discounts that can go with that. And here we can see a live measurement. Now keep in mind that the internal phase noise of these spectrum analyzers are already pretty low. That makes the cross correlation run obviously faster, and with the appropriate cross correlations at a 10 megahertz offset, we're looking at almost minus 180 dBc. So even some of the most challenging crystal oscillators can be characterized. And because this PN400 is connected directly to the input of the spectrum analyzers, you're essentially limited only by the frequency range of the spectrum analyzer, in this case with the appropriate cabling, of course. You can go all the way to 40 gigahertz, above 40 gigahertz. So it's a new combination with the software. I think a pretty powerful idea, and I think an interesting business case because of the flexibility of being able to disassemble this and put it back together and use it in multiple different scenarios. And we also now have a brand new VNA 400, which is a 40 gigahertz two-port network analyzer that Siglent has also released. This is a purely USB-powered unit, under 15 watts, just connected with the USB in the back, which makes it a lot easier to use in the field. You can just plug it into the computer and it'll be ready to go. We're looking at about minus 135 dB of dynamic range in the low frequency, minus 120 dB of dynamic range in the higher frequency. And the software is written with the same fast-paced GUI interface that you see. I really like the Siglent Hound software because it's lightweight and it runs really well, and you can see this is clearly an extension of their platform. They're beginning to have quite a rich set of GUI interfaces. So I'm sure there will be other versions and variations of this, but being able to plug something like this directly to the computer with a USB and run it right on there and disconnect it quite easily is a huge advantage. So hopefully we'll get our hands on this and do some experiments of our own. And here in this station, we're taking advantage of the API interfaces of the Spike software that's already available with various switch control capabilities and support built in there, so you can start running your own script and create an automated test setup. This is an example of this just to demonstrate the idea, but the Spike software itself, because it does have that open API, you can essentially write anything you want and connect it to any combination of these devices that you want and synchronize them. But being able to do this in kind of a support directly from the manufacturer allows you to now expand automated testing using their ever-growing set of equipment. So here at Millibox, we see now their reflector array set up for measuring near field to far field and using the parabolic conversion. Now Millibox is a very interesting setup because pretty much everything is 3D printed and scalable. So depending on the size of the chamber you're looking for, you basically assemble the size that you want. You're buying it in a modular way. These are super helpful in the lab. We actually use it ourselves quite a bit in one of our setups. So in the far back, you can see the reflector. In this particular measurement, you see the actual DUT moving around. There is a 20 dB horn antenna that is mounted in the front. This is a D-band setup. So with the movement and complete 3D rotation, and with the instrument connected to it, you get the profile, the radiation pattern profile of this particular lens that's out there. Now, because this is all 3D printed and flexible, you can imagine that as new things become available, new devices and parts and modules become available, you just add it to your system and you make it continue to grow. Now, Millibox also does a lot of work with universities, so there's actually a competition that happens here at IMS where students get to design and 3D print some kind of a horn antenna, and whoever has the highest gain measured here in their setup will win a prize, and I think the prize is this cool radiation pattern of a phased array. So yeah, these setups, because they're flexible and inexpensive and modular, definitely a good platform for education and university use as well. And here at MPI, we have the MPI terahertz selection probe station. So what do you want from an ideal probe station? Well, you want it to, of course, be reconfigurable, so you could add essentially any vendor heads that you want to it. And this probe station will support VDI, will support Rod and Schwarz, will support anybody that you want to add, and they come down very close to the probe interface to the wafer. Now, there's a few unique features about the way this probing system actually works, is that it supports down to minus 60 degrees Celsius directly in an open environment. And they do this by making sure that there is appropriate laminar airflow above and below where the chuck is cooled down so that you don't get any frosting and you don't get any condensation. We do have a full digital camera in the front with a large working distance. A large working distance on these microscopes is pretty important because in a waveguide setup, you have the rigid waveguides coming out of the probe. And because there are so many circuit configurations and you don't know where your probes are going to be, you want to make sure you have enough clearance to actually see what you're doing. And especially with a fully digital camera like this, and things can be moving around, you want to make sure nothing crashes. We do have a wafer loader here on the side. You can do fully automatic wafer loading, or you just don't want this, you can leave that one on the side. We have the cooling and heating station over there, and we have the software that controls the entire probe station. In this particular measurement, they were measuring a distributed amplifier, very broad band, and they were measuring it at D-band, actually putting modulated signals through at 100 gigabit per second of modulated data directly live on the probe station going through the circuit. Earlier, that was the demonstration. Now, at the same time, because the entire MPI ecosystem of probe station is flexible, there are many other variations of this probe station you can have. There is heavier bases for the hexapod control for optical measurements. There is the broken down versions of these, which if you don't want a very big probe station, that's also supported. But yeah, every year I come here and I see MPI has done something new with their probe station, supporting even more vendors. The software is free for life, is all connected to any vendor you want, any spectrum analyzer, any network analyzer. Really a huge ecosystem of parts available now. So here at Junkosha, we continue to see that they push the boundaries of their cables and improve their materials. That's one of the main advantages that Junkosha has, is because they essentially manufacture, from a material point of view, everything in the cable itself, so they can engineer the PTFE material, the shielding, the connectors, and everything. And look how flexible this cable is. I mean, that's crazy. This is a 1 millimeter cable supporting up to 110 gigahertz. Super flexible, which is really helpful nowadays because there's so many interfaces with 1 millimeter. You don't want any strain on these connectors. You want them to be able to flex them around and connect them easier without degrading the phase and the magnitude of the insertion loss of this, which is very, very stable, even though it is so flexible. At the same time, they can make that, this is a more rigid version of that cable, but they can make this also flexible. This is now a 0.8 millimeter connector, which is very hard to see on camera, but this would go all the way to 145 gigahertz. And in particular, with any heads that do support that frequency range, you can do a single sweep up to 145 gigahertz. Yeah, huge advantage being able to manufacture every aspect of the cable yourself, because you can engineer it to almost any circumstance. And Junkosha is now also launching a dedicated network analyzer cable. You can see with this characteristic very thick shielding for that it can be quite stable. Now, despite the fact that it is such a big cable and intended for metrology, it does have a bend radius of 57 millimeter and a phase stability of maximum of 8.9 degrees. So of course, in a setup like this, you never want to bend it that much after it's been calibrated, but it's nice to see that it is as stable as it is. It's the same core technology of the PTFE material, and of course engineering the entire cable from end to end, now bringing the metrology grade network analyzer connectors as well. And here I am at AARONIA, and they actually have a new V6 real-time spectrum analyzer that's coming out. This one is going to go from 9 kilohertz to 110 gigahertz, which is absolutely insane. But on top of that, you do still get the 3 terahertz per second sweep rate, and the new version of this will have 490 megahertz digitization gapless streaming. I mean, consider for a moment what this implies. It means that you can look at spectrum from 9 kilohertz to 110, everything that's over the air, and gaplessly pick the frequency you want, 490, transmit it, record it, save it, and process it, all with rapid switching between the frequencies. I don't think there's anything like this on the market. And we'll talk about the software in a second, because that's this whole other domain. There's another version of it, 18 gigahertz as well over there. This one is a 1 millimeter connector, but they will also have the waveguide version so that they're more ruggedized and banded, and perhaps a little bit better performance in a specific band you're looking for. But just the size of this would mean that you can cascade them, you can put them into a grid. Yeah, this is an extraordinary piece of engineering. I can't wait to get my hand on this. In this example, they're looking at a 77 gigahertz FMCW radar signal and a 24 gigahertz simultaneously. You can pick him, you can demodulate, you can analyze. It's just amazing that this is possible at this level of integration. And here we're looking at this massive display that's showing all the capabilities of the RTSA Signal Pro, which is the software that runs and analyzes all the data coming from the real-time spectrum analyzers. This is almost overwhelming in terms of the number of features and capabilities it has. To just give you a few ideas, here we're capturing a whole bunch of different signals, and the software is capturing it, recording it, demodulating it, classifying it, and then storing it. And because it's storing it per event, per detected event, it's not storing it on the hard drive, all the signals that you're not interested in, you're basically only storing what is of value. Here on the right side, you can see all the different plugins that are available in the software, and at the top, you can see an example how it is building a signal flow. And with that signal flow, you basically bring it all together and you build the setup that you want. There are so many permutations possible. And once everything is recorded and stored on the hard drive, you can then go and look at each individual event and then analyze it further if you want to. Now at the same time, this is running on just a regular AMD processor, multi-core processor. You don't need a very expensive GPU to do this. It's running remarkably fast, given how much stuff that's happening in the background, testament to the efficiency of the software. But I think it's going to take about a year to learn everything that this software can do. But the ease of putting it all together and just having access to your fingertip is quite amazing. So now we're beginning to see more and more various vendors push the boundary of what you can do, load pull on at the frequency ranges. So now D-band being somewhat of a common frequency range nowadays, you can have a D-band tuner that fits very close to the probe. A few advantages. So this unit itself has about 0.9 coverage on the Smith chart, but of course the losses of the probe would limit that. But bringing this so close to the probe interface means that you can get as much of the tuning capability on the Smith chart from each of these modules as possible. We have the coupler access directly there. In this particular example is connected to a Roden-Schwarz head. But you can see that these probe stations for MPI are of course reconfigurable in any different band. But here at Focus, they want to make sure that they are going to give you all the tools ahead of time so that when you do PA design, LNA design, and so on, that you can actually characterize all that load pull at these very high frequencies, something that I see more and more of it here on the booth, and there's a few other examples of it. These ones go even higher in frequency. I think this is the highest frequency one, yeah, 330 gigahertz, which is quite amazing to be able to fit this into the same form factor across all the different bands with the waveguide access, giving you excellent performance across load pull for all these frequencies. Now measuring noise at D-band is a whole other problem, primarily because there are so many uncertainties that come up on top of each other at these higher frequencies, because every loss in the system is going to make things more difficult. For example, if you consider frequency down converters, as good as they are, they still have a considerable conversion loss and noise figure inherently. So in this setup where they're measuring D-band noise, they do have a front-end module specifically for noise measurement, where internally we have a low noise amplifier and essentially signal conditioning to make sure that you get the best repeatability of the noise directly measured at this. Look at the distance between the front end of this and the probe itself. So here in this setup, they're measuring 110 to 170 noise figure. There was actually a live demo and a publication that went with it. You can see the different measurements here. It's a little bit hard to see on camera, but there are several dies that are measured here next to each other. We're looking at a noise figure of 5.1 dB, which is all measured directly on this setup. At the same time, there's an RF switch in the front that can switch the noise source or the front end into the probe. There's so many unknowns on top of each other. I mean, measuring noise itself is not difficult, but measuring noise that's repeatable, where you don't have much control over the ENR of the noise source, or you don't know what kind of noise your circuit has, or you have a, let's say, a high noise or a low noise circuit that you want to measure in the same setup, that's where the challenge comes in. And this publication and this demo focuses on these repeatable, reliable, low uncertainty noise figure setups. And here at VDI, we see their frequency extenders and network analyzer modules. Of course, they can go up to hundreds and hundreds of gigahertz, but these new miniaturized versions of the WR65 110 to 170 have been quite nice. We're using them regularly. In this setup, we have a 3-port network analysis, so there are a few things are being measured at the same time. First, we have their latest PA. I think this was there last year as well. This is an 8-way power combining indium phosphide, putting out over 1 watt of power at D-band, which is quite extraordinary. And then after that, we do have a circulator. So you essentially have two paths. You can have the signal going through this way, you can have the signal going through in the front, and of course the reverse in both directions as well. So you're getting all this characterization at the same time. And one of the miniaturized versions of these allows you to actually bring these setups pretty close together, which itself is quite difficult. They're compatible with the Keysight. They have the firmware inside the Keysight to communicate with them, and it becomes almost a seamless setup. You can see even customized cables that go directly into the PNA millimeter wave test set connected to it. Very nice. The new versions of the WR6.5 do have indium phosphide power combiners at the output as well. There are now 20 dBm, and I believe there's another version of it that goes even higher. Very important to get high output power from network analyzer extensions, because you often are measuring passives and you may have a lot of loss. And a lot of power also means that you can do power measurements and do OIP3 and compression measurements, actually be able to drive amplifiers that typically don't have a lot of gain into compression directly from the unit within an external PA. So very nice and helpful setup. Now for field use, the Keysight FieldFlux is a very popular handheld device. We've looked at this extensively on my channel and in other places as well. And it's nice to be able to have devices that plug directly into this. And it's pretty important in the field because you don't want to have cables or anything else around. You just want to directly attach this. And these extenders are also now available from VDI. This particular one is between 60 to 90 gigahertz, and you can connect it directly onto the FieldFlux, and all the coefficients and everything will be set up. So essentially extending the frequency of the FieldFlux 9 to event quite easily. And this is a 26.5 gigahertz instrument, so obviously multiplication, a factor of 6 is used here to be able to do this. And using this technique with various horn antennas, you can now do OTA measurements directly in the field using multiple FieldFlux. And here we're seeing a little bit of an insight on how VDI plans to get to frequencies above 1 terahertz. So this is actually a 2 terahertz setup, which itself is quite crazy. So we have a 170 to 260 gigahertz multiplier front end that goes into a power amplifier, also indium phosphide, and then that gets multiplied by 3 and then multiplied by 3 again. So you have a factor of 9 multiplication, which of course with this will take you over to 2 terahertz. And then over here we do have the prototype version of a 2 terahertz down converter. So now you have a complete 2 terahertz system. In the near future, all these building blocks will be integrated into another type of these modules, and then you will be able to do 2 terahertz S parameter measurements in the future. But it's kind of nice to see the thinking process and how they constantly evolve the process to push themselves into these higher frequency bands. So here a few new products from MiWave. We do have a few different versions of these attenuators. Now in a waveguide setup, to be able to have a predictable attenuation is actually quite difficult, and the reason is because all of these micrometer-based attenuators do not have a linear range of attenuation with the depth of the micrometer, and so you have to have some correction. You have to pre-calibrate this, know exactly where you are in the depth, and then that will be your attenuation. The nice thing is that in this unit, they've done that, and they've done that to 0.01 dB of step. This is a W band, but they go all the way up to J band, which is kind of crazy to think about, that you will be able to control and repeatable attenuation adjustments. And because they're waveguide stable, it also makes your entire setup, of course, much more predictable. You can also have a manual one. So this has a readback directly from the location of this. So this is an optical encoder, most likely, driving the plunger, the micrometer inside, and you get a direct readback, so you can quickly adjust the attenuation. Very nice. And this is of course the old version of it where everything is manual, but this is super helpful if you want to do a repeated measurement and you want to go between large dynamic range of attenuation. We do have fixed attenuators, we have high power attenuators, and we do have electromechanical switches to switch various waveguide ports. So these combinations are quite useful in the lab, especially if you want to move things around. And if you look at this one even has a built-in battery, which is quite nice. So you can remove it, put it somewhere, do your measurements quickly, and this probably should last quite a long time, because the only time the motors are engaged is when you change the attenuator. Otherwise, it's just sitting in standby, and all you're really running is the LCD. So very nice idea to have that battery powered as well, and you have leg adjustments, so you can bring the height to where you want. Cool products. And in case you're curious, this is a 70 dB dynamic range. It's actually F band, not W band of control. And as you get to higher and higher frequencies, you will have a slightly less range of attenuation control, probably about 50 dB at higher frequencies. But 70 dB is a very large amount of attenuation. And of course, you can always cascade these and put 2 of them in a row. You'll have 140 dB if you need that much attenuation. So another area that MiWave has focused on is making high power amplifiers, but particularly given the situation globally, to make sure that this is entirely manufactured from design to semiconductor to assembly here in the United States. So they have various high power amplifiers covering broad ranges 1 to 26. We do have other bands as well, and it goes all the way up to, in the future, D band and above. And these amplifiers, knowing the history of where the amplifier came from and being able to track where it was made is obviously important for military applications, and this is another area that they've been focusing on. And here at Flann, we do have a whole new set of various waveguide and transitions that I'd like to talk about. A few things right off the bat. These waveguide switches are remarkably small. If you look at some of the other waveguide switches I showed earlier, this has been really miniaturized, and this allows you to build this compact setup a lot easier. They do have these flexible waveguides that you can flex a few times and set into place, but they still will have essentially the same loss characteristics as a regular piece of waveguide, but now you have the complete freedom to bend them in these unusual angles once you want to set up your setup and then fix it in place. We do have a full band OMT conversion, which is also pretty new. We do have two different attenuators here, a precision attenuator and a piezoelectric driven attenuator, which is also really, really small, making things compact at D-band. And in fact, if you go to higher frequency, you would want them to be even more compact, because as you can see how closely coupled this setup is. And they have another piece here, which I actually never seen before. Here they have a coaxial cable that has a direct transition to D-band. But this is a full 110 to 170 gigahertz coaxial transition. There's no connector. These pieces come out together. In this distance, you're talking about 5 or 6 dB of loss, but I mean, this is super flexible and thin. I've never seen something like that. That's quite interesting. And at the same time, this whole setup, obviously compatible with VDI or any other thing you want. You can build these really complicated waveguide setups. They do have a live measurement here through the over-the-air measurement. You can see that it is all going. Really nice devices. Definitely have to check them out further. And here at Eravant, the number of components they have continues to grow. So this is their D-band setup. I think we saw this last year, D-band network analyzer in conjunction with the PNA-X from Keysight. But now they have this rotary joint, high-power rotary joint. Look at this. This is a D-band interface. And look how stable the S parameter is as I rotate this. So you can imagine this is super helpful in situations where you have, for example, some measurement you're trying to do and you're trying to move things around, but there's a lot of cables in the way. Waveguides are, of course, can't rotate 360 degrees normally, but this allows you to connect everything with the flexibility and move things around. Very stable, even in metrology. Very nice device. And also the number of active devices that Eravant makes is also continuing to grow. This is their frequency multiplier with the micrometer attenuator, and this is a down converter mixer. Basically is a front end that you can connect to a spectrum analyzer with a single port where the LO and the IF are superimposed. In this test, they're not connecting it to the right instrument at the moment, but essentially what you will have is a single cable that goes into the LO-IF port of a spectrum analyzer, and then this becomes the extender front end of that. They have a lot of different active elements and devices that they continue producing, from amplifiers, up converters, down converters. They're covering all the way to the J-band. They can do network analyzer, and their portfolio continues to grow, which is quite impressive. So here at Tabor Electronics, I do have an interesting demo that they're doing in conjunction with Rutgers University. So what they've done is that they have taken a few of these arbitrary waveform generator modules that they have. These actually have built-in digitizers as well. They compete with the M8190 in terms of the performance, but they're this broadband, essentially software-defined radios, and you can generate any waveform you want. So you can now start experimenting with what you can do in millimeter wave signal propagation and coding and how you want to build future networks, and that's what is done in conjunction with Rutgers. There's actually a live demo running. There's a transmitter over there, and all the way on the other side, we have the opposite, the receiver. And because you have full control over the API and you can run your own script and you can write your own code, you can generate any waveform you want. You can combine them and analyze them and figure out how you can de-embed them from each other. It becomes a platform, not just in terms of the millimeter wave capabilities itself, but also in terms of signal processing and how you code things and decode them and how you would deploy them in the field. And you can mix and match them with essentially anybody because it's almost open in that sense. So this is becoming more and more of a powerful platform for future research as well as practical industrial applications. So here at Swiss 212, we have a whole bunch of interesting metal printing technology used for microwave and higher frequency bands. So the fundamental idea here is that if you could print metal directly from a 3D printer with a custom firmware at the feature sizes you're looking for, you can start to make what are essentially impossible features directly in one piece. So you can have filters and diplexers and transitions and waveguides, even a combination of a whole bunch of them into one flange with all the interfaces at the same time, which would be impossible to machine. This will be significantly lighter. It would be cheaper to manufacture. You can do all these crazy transitions in between without incurring the loss and the machining required to put everything together. They've also explored even higher frequencies up to Q and V band. You can see these features continue to get smaller and smaller. But imagine that you want to create a very complex filter bank that has 2 or 4 different frequencies at the same time. You want to transition in and out of that. How would you go about doing that using a CNC? You would have to build it in pieces. Here you're growing this all at the same time. So all of this starts from a powder, and the powder is planarized, and then you have a laser that binds it together, and then you grow it layer by layer and by layer. So the business model currently appears to be that if you have a particular design, you would submit, they will manufacture, build it like this for you. I think something like this takes about 10 to 12 hours to print, and then you'll have these unusual feature sizes, and they're looking at going at even higher and higher frequencies. So if you have a totally custom design, this would be an interesting way to do it. Just one thing wanted to clarify is that the way they operate is that you would have a certain specification and requirements for a system that you want to accomplish, and you would give them, they have the engineers and the expertise, know-how both on the material as well as the design to realize something like this based on your D, so you can directly put it into your system. And here at Maury, we're going to look at their passive and active load pull system as well. We see actually a few of these already. Quite a few companies are doing this at the same time because of the importance of being able to do load pull on these complex 5G systems, to be able to make sure that these PAs, especially across phased array configurations, across active return loss configuration, are going to perform what you're expecting them to do. The interesting configuration here is that you do have these 2 tuners directly as close as possible to the probe, so you do get 0.85 coverage on the Smith chart in passive mode, and then you do have the active terminal directly connected, and once you have the active terminal, you can inject your own signal, and then of course you can do anything you want. Then you would be in the active load pull region. The entire setup being compact and to the probe allows you to cover, I believe this one is 18 to 50 gigahertz, and all with their own software, fully written and fully characterized. You can quickly get your calibration, you can switch back and forth between active and passive, and go through a huge range of measurements with scripting and all recorded. Very nice setup. So of course we know that from VDI you can get frequency extenders to almost any frequency. We saw now at a 2 terahertz version, a prototype as well. So what you really want to do is, if you own all the system, you want to find a way to be able to do load pull using these extenders already with the equipment you have and with the PNX you have. So here what Maury is doing is that they're controlling the phase and the amplitude of the signal that goes into the up converters. So you're basically controlling the IF signal, but because you control them after calibration, you can create an incident wave that you want directly at the output or input of your device that you're testing. So you can create a load pull situation now using these extenders without having to worry about anything else in the background. You calibrate, and then you pick up whichever one you want. You have all the script written, all the calibrations available. You can do load pull on the Smith chart, 110 to 170 or even higher bands. It's become so much easier to do these load pull measurements, especially active ones. Active load pull measurements certainly have come a long way, but making a simple system to leverage what you already own, I think that's a pretty good idea. Now, making noise figure measurements is already very difficult, and extracting noise parameters like gamma opt is even more difficult. But now here's another challenge. Imagine you have to do this in cryogenic temperatures. Of course, all the mechanical tuners and so on can no longer be put at those temperatures for many reasons. One is that the heat lift of these kind of coolers is already fairly limited. So here what we have is a completely solid state tuners that are required for noise parameter measurements. It can be enclosed down to 4 Kelvin. So being able to extract these parameters at high frequency, very difficult. So of course these are very esoteric and very specific needs, but if you need to be able to extract noise parameters, particularly for quantum applications, for example, at these frequencies, this is how you do it. So how about an end-to-end solution, everything included for active load pull at remarkable speeds? So here we have MT2000F platform, and this is a 700 megahertz to 67 gigahertz system that supports a 1 gigahertz bandwidth for active load pull. So in one setup, you basically do everything. You can measure, go around the Smith chart, do all your typical active load pull that you do, but you can also measure things like compression, ACPR, and because you do have that 1 gigahertz modulation capability, you can now look at your constellation across load pull conditions, which is ultimately at the end what you're really looking for, because that's going to determine the signal to noise ratio of the entire link across those load pull situations. Everything together, super fast, all in under one. Of course, when you own every piece of the system, you can make it super optimized, but then it's a one-stop to make all these measurements in one go. So here's something interesting from Copper Mountain. So they do have a whole set of USB-based network analyzers, but the modules that are at the heart of those network analyzers are actually quite small. So this is a 1 gigahertz tiny little VNA module there that you can use in a variety of applications. They have a larger one that's a 2-port one that goes up to 5 gigahertz. Now because of their size, they can be embedded in various places like for food safety and for detecting moisture, even figuring out how much moisture is in a peanut bag so that you can estimate its lifespan. So this miniaturization also means that the cost will come down and you can put them in all kind of devices, and this is just a little setup to show that this works, but it's essentially taking the heart of the technology they have and applying it to a wider industry. It's a pretty cool module. And here's a new redesigned network analyzer platform that is going to be available in about a year or so. And this platform has access to all the receivers separately up to 22 gigahertz, which means that you can, of course, put signals into the receivers and allows you to do all the things that extensions allow you to do. But on top of that, at the back, you have the ability to connect to millimeter wave extenders. Now, because of the close collaboration between Copper Mountain and Eravant, this would mean that a platform like this, combined with their frequency extenders, now all of a sudden becomes a super fast and flexible network analyzer platform all the way to hundreds of gigahertz as this becomes available next year. So looking forward to take a look at it. So here again at Microsanj, I've actually recorded a few of these videos in the past, but here they're measuring a gallium nitride amplifier device directly on their system. Now if you think about the primary limitation of making general thermal measurements using infrared is that the speed of those measurements is slow, and the resolution is slow because you need a silicon lens to do that. But in this case, you're measuring it in the wavelength that allows you to use typical optics to get the resolution you want. So you're simultaneously looking at your device in the visible spectrum, but you're also using the Microsanj pulse laser approach to extract the thermal information as well. So now you're down to 250 nanometer resolution, 500 picosecond timing. So this has some interesting implications on making semiconductor measurements, because now you can look at a gallium nitride amplifier, you can turn it on and off really rapidly, you can put modulation signal through it, and you look at the thermal flow during the active measurement, which is not something you can do typically. But at the same time, you can see it directly on the camera as well. So the physics of this is a whole other thing, and I think we should cover that on the channel separately, but the ability to be able to make these measurements at this speed is a very important aspect of this entire system. There is another measurement they're doing which unfortunately doesn't have a live demo, but they're able to look at a phased array antenna, and let's say they have 64 antennas, and they can rapidly measure EM emissions through their thermal measurement. So you can quickly find out if a large-scale phased array has bad elements or it has some PAs that are not properly connected to the antennas, and you can do this rapidly in a production environment without doing any RF measurement, which is very different. So I'm curious to see how this will be deployed at large scale, but it's one of my favorite technologies on the show. So here at EV Technologies, we see a live demo running of a measurement platform that I think is quite interesting. So they do have a switch matrix correlator here that is directly connected to the network analyzer. And there's 100 dB of isolation up to 30 gigahertz between each of these ports. So which means that you can use a multi-port network analyzer and connect it to a very complex antenna structure, and at the same time be able to switch between all different permutations and combinations and make it really 3D, essentially a matrix of measurements across all the different parameters. At the back we have the Roden-Schwarz reflector. I think you've seen that before. It's a near field to far field translate, a very, very smooth mirror that can operate up to tens of gigahertz at the same time. And they also make these modules. This is a phased array module with all the active circuitry inside of this box and the antennas in the front operating up to 30 gigahertz. And you can see because the thickness of this is proportionate to the size of the antennas themselves, this entire thing is 2D stackable, and you maintain your antenna spacing and you maintain your radiation pattern, and all the thermal and isolation and everything is handled in here. The isolation 100 dB in these modules is accomplished via a very specific gasketing technique they have in their devices. Can actually take a look at it here. There it is, and that allows you to get this 100 dB isolation. It looks like this is this almost looks like it's printed or
this is a
deposited.
gasketing developed by EECL, our partner.
Right.
UK.
Yeah, it's developed in the United Kingdom, and yeah, that gives you this extraordinary high isolation. So all these technologies come together in this setup. So now extending the performance and capabilities of their vector network analyzer, Siglent is now showing a 4-port network analyzer up to 26.5 gigahertz with port extension capability in the front. So this has now about 130 dB of dynamic range and of course the 4-port access, and it should be working when it's released with the Eravant frequency extender. So now basically you have Siglent being able to use their VNA platform to measure hundreds of gigahertz in conjunction with the Eravant modules, which is pretty cool. It does have electromechanical attenuators in, as you can do output power control, and everything that you would expect from a 4-port network analyzer. So now this, in combination with the other network analyzers that I have reviewed on the channel, becomes a full product range across different price points and performance depending on how you want to deploy it. And now we have the handheld spectrum analyzer, network analyzer combination as well, up to 26.5 gigahertz. This is actually a complete 2-port system, so you can do full 2-port network analyzer directly on the module, over 100 dB of dynamic range, of course portable, handheld. How long does the battery on this last, typically? 4 hours of operation, up to 26.5 gigahertz. Now it's and if you notice, all the software across the entire product portfolio is the same. So that's got that consistency which all the vendors are looking for. It's nice to see here too. And recently we've seen an entire new lineup of 12-bit oscilloscopes from 70 megahertz all the way up to 4 gigahertz, which this particular model is on 4 channels. I'm not sure which ADC is inside of this, but of course the 12-bit ADC in this form factor would be quite nice. And there's a whole bunch of software solutions that sit on top of this for compliance testing and mass testing. You can see one of them running over here. I actually don't have any of these in my lab, but I've heard some good things about the digital storage oscilloscopes that Siglent has. We have a whole bunch of setups and experiments we're going to do in the future, but it's nice to see a 4 gigahertz 12-bit oscilloscope. So here on the Tektronix booth, they're combining the AWG7000 with one of their real-time spectrum analyzers here at a carrier of 10 gigahertz. So often in these very complex signal generation in the RF domain, it's difficult to separate various RF events from each other, and that's because everything is mixed together. So you need advanced triggering and advanced signal processing techniques to be able to extract a signal piece of information. So here in this example, they have a step chirp that's going through, and there's some anomaly or some event that inside of that is buried into this complex waveform that's coming on and passing at hundreds of times a second, and need to figure it out and bring that out. And because they have this extremely fast capture and all these advanced triggering mechanisms, things like triggering on a frequency mass, triggering on the RF input, or on the density of the phosphorus density that you see over here, you can bring all that features out directly on the software. And all of that is streamed into the computer and processed directly on the computer. And in my view, the Tektronix, especially their oscilloscopes also, are some of the most advanced software platforms for catching these extremely unusual events. They seem to be able to combine kind of frequency domain thinking and time domain thinking very well in their instruments to be able to catch these things. For instance, something else that shows this ability to relate time and frequency events together, there's a time qualified trigger capability as well that allows you to define how short these pulses you want to be in order to catch them. But remember, these pulses are happening in the RF domain, right? It's not the same as an oscilloscope that you want to catch a pulse in the time domain. Here you have something that's modulated and being down converted, but you're again treating them all the same way, which is a powerful platform. And of course, once you have really good down converters and real-time spectrum analyzers, you can work with someone else's software to perform additional analysis. So here there's a collaboration with DeepSig, and DeepSig has an AI-based neural network that looks at the streaming data coming from the spectrum analyzer, analyzes it based on known protocols, wireless protocols, captures them in real time in a GPU as it is running, and then creating an entire statistical distribution and events as they're happening in real time. So you can imagine, of course, if you build these things and you work with a strong AI software platform, you can now pretty much do anything, even on waveforms that would be buried or very unusual, for safety, for security, for detecting unwanted devices that may be around, or just figuring out how various things interact with each other, sharing the same spectrum. And here I'm at UNI-T, and they're actually coming into the United States as well, so they're now bringing their instruments here at the show, showing some of the capabilities they have. They have a 4-channel power supply. They do have 12-bit 500 megahertz oscilloscopes, 4-channel again. They do have an 8.4 gigahertz spectrum analyzer, pretty fast, 100, and the other one, the 26.5 on 100,000 measurements a second. So this complete portfolio of instruments now basically competes with a pretty aggressive market that these instruments are in now, but the prices are very aggressive. They clearly want to capture some of the North American market. The GUIs of these instruments are very nice. I've used them a little bit myself. Hopefully we'll get a hands on these and try them out in the lab. But to be able to enter the market, and say here's a 26.5 gigahertz spectrum analyzer, minus 163 dBm, displayed average noise level, 100,000 measurements, and 100 megahertz of analysis bandwidth as the first thing you bring to the market in North America, that's pretty good. So I'm going to be eager to see that. Unfortunately, that doesn't turn on yet because it's going to be released sometime in August. That's just a prototype, but very nice looking instruments, all unified. And so here I am on GGB. Of course, everybody knows them. They have a variety of probing solutions and custom probing solutions that we use quite regularly. This is their probe going all the way to 1.1 terahertz. I like the design of these, and if you look at the way they have managed the mechanical support of these probes, especially often with the big weight that has to be there, it's a nice design. You never want that to flex as it moves around the surface of the chip that you're trying to measure. So I like that combination. And they've also expanded their manufacturing facility so that the lead time would be shorter, which is something I think everybody would appreciate. But if you look at their portfolio, there's pretty much every combination of probe you'd ever want to build, going all the way to 1.1 terahertz. So here I'm at Presidio. Of course, used a lot of their components over the years, but I just learned something new that I wanted to share with you. So they're making capacitors for cryogenic applications, as these devices are now more and more in demand for devices that are cooled all the way down to 4 Kelvin and still have to maintain capacitance. Typical multi-layer ceramic capacitors, their capacitance goes down rapidly as the temperature goes down. But the dielectric material they're using here does the opposite. So the temperature actually increases the dielectric constant. So you have a capacitor that exhibits much more capacitance at 4 degree Kelvin than it does at room temperature, which is pretty unusual. They have a whole bunch of these 3D printed devices that shows the multi-layer capacitors interacting with each other, which is also interesting. And they of course make O201 devices with very, very high quality factors that many people use for DC blocks across various frequencies, quality factors in the tens of thousands. Yeah, they're one of the main leaders in the industry making these kind of capacitors, but this new line of cryogenic CRX, very cool devices. And here's a closer look at what happens. So here's the room temperature, this is temperature in Kelvin. As you go down, you get a little bit of an increase, but as you go to these really low temperatures, close to liquid helium temperature, you get to these really high value capacitances. Very unusual device, and of course, aside from cryogenics, there's space applications and other harsh environments. But it's interesting to see that there are materials that do the opposite of dielectric constant trend than they do at room temperature. So here, RF-Lambda, they're known for a wide range of high-power broadband amplifiers. You can see a whole different sequence of them. They actually make them all the way up to hundreds of watts, but these are the smaller modules here on display. Various inputs and output characteristic, waveguide input and output, for example, on this unit over here, broadband 18 to 40 gigahertz. They have some really popular sub-6 gigahertz one for obvious reasons. They fit into 5G and 6G ecosystems. They have a kind of a similar interface in all of them, efficient, high power. You can deploy them in any situation you want, and because they have such a wide range of products, they would fit a wide range of applications, of course, up to hundreds of watts. So when it comes to rapid switching, it's hard to beat something like this. So this is a 160 throw pin diode based switch matrix. And of course, if you need to switch that many things in 50 nanoseconds, there are not that many technologies that can do that. You can see the TTL interface in the front and the input. So the compactness and the rapid switching of this has a wide range of applications. This one goes from 0.05 to 20 gigahertz. And given the number of ports and the way it is organized, you could imagine phased arrays or antenna switching or any kind of places in automated testing where you want to deploy that. There are not that many switches this broadband with this many ports. I don't think I've ever seen one this complicated, but they also have a whole bunch of other switches, the electromechanical as well as solid state ones, for a wide range of frequency and different configurations depending on the customer needs. So here with IronWood Electronics, I want to show you an interesting temperature cycling system they have. So the key here is that you have a remote head with a very low thermal mass that you can bring very close to your device under test, particularly inside of a package. So in that package, you would bring this and close it down and it will be a completely enclosed system, and you can rapidly bring the temperature. So here we have set the temperature to -40, you can see it's rapidly going down. But this system allows you to not have to put something in a temperature chamber because you have this localized low thermal mass head. The low thermal mass also means that it's comparable to your device under test, so that enables the really rapid up and down temperature cycling. So with the appropriate socket, you can imagine putting a die in there with a direct connection with a very low low thermal resistance between those two, so the temperature of your die and the temperature of the cold head or the hot head will be pretty close to each other. And you can cycle this up and down across 100 to 200 degree, which is quite a lot, and it can happen very fast. It's a pretty cool form factor. I don't think I've ever seen something in this size. Most likely it is solid state, of course, because it looks like it was probably Peltier based, that allows you to run it very, very quickly. And there you have it. I hope you enjoyed it. Next year, IMS will be held in San Francisco on the west coast of the United States. And I'll certainly be there, and perhaps we can catch up in person. See you next time.